So this video is going to pick up right where the last one left off. So we had just finished up example 10 and we're going to move on to example 11. So we're going to consider this reaction. Remember that when we're changing pressure, an increase in pressure is going to favor the side with fewer moles of gas. And if we decrease the pressure, it's going to favor the side with a greater number of moles of gas. So you're just adding up the coefficients on each side. So in this case, on the left, CO2 has 1 mole, H2 has 1 mole, so a total of 2 moles on the left. And then if we look on the right side, the CO, carbon monoxide, is 1 mole, and the water is in gas form, so it's another mole. So we have 2 versus 2. So a decrease in pressure, which would typically favor the side towards the greater number of moles, is actually going to have no shift at all here because there's no advantage for one side over the other. Okay? So moving on to the next concept, out of all the stresses, increasing pressure or decreasing pressure, increasing temperature, decreasing temperature, and then increasing and decreasing concentration, the last thing you can do to a equilibrium system is add a catalyst. But in adding an addition of a catalyst is actually not going to cause a shift in the reaction. Instead, it's going to make the reaction reach equilibrium a little bit faster. Because remember, what happens when we add a catalyst is it both speeds up the forward and the reverse reaction. And when you speed up both at the same time, you reach equilibrium faster, but you don't cause a shift, okay? But the really cool thing is you can use Le Chatelier's principle and the use of a catalyst to affect the amount of yield of product that will be. And if you're thinking about this as like a big company who's trying to make a lot of money and the product you're making is something that you need a lot of, if you can make that faster and you can make more of it by increasing things like the temperature or decreasing the temperature or adding a catalyst, that's something you really are interested in. So altering the yield is a very important part of chemistry. And so the yield of product could be increased if the reaction shifts towards the product side. So if we increase the forward reaction. So we'll take this first system here. If we wanted to alter the yield here, let's say NH3 is really useful and we really want a lot of it. So if we had this system, how could we manipulate it? Well, in the first scenario, if we added or decreased more N2, what would happen? Well, if we think about this, N2 is over here on the left as a reactant. So if I added more of it, then that's going to cause an overload in this side and cause it to shift to the right. So that's definitely going to help us create more NH3. But let's check, would removing N2 do the same thing? Well, if I removed N2, that's going to create a void, and that's going to cause it to shift back to the left. So that's actually not going to work. So adding more N2 would actually really help us alter the yield towards the product. All right, what about pressure? Well, we have 3 moles here, 1 mole here, so a total of 4 moles on the left on the reactant side. Over on the right side, we have 2 moles, so 4 versus 2. Remember that increasing pressure goes towards the side with fewer moles, decreasing pressure goes towards the side with greater moles. So in this case, 4 versus 2, we want to go towards the side with 2, so we want to go towards the side with fewer moles, so we're going to increase our pressure. And last, would we increase or decrease the temperature? Well, looking at our delta H, our heat, we see it's negative, so that means heat belongs over here with NH3 as an exothermic reaction. So we know that if we increased the heat here, we're going to cause an imbalance on the right side and cause it to shift back to the left. So instead, we want to create a void over on the right side. So by removing some of the heat, by decreasing the temperature, we're actually going to create a shift towards the right, towards the product. So in this scenario, I could add more N2, increase the pressure, and decrease the temperature. And by doing that, or heck, all 3, I could very much increase the yield of NH3. And in some cases, if I were a big company and making NH3 was super profitable, I could increase my profits. So, what are some other things I need to know about calculating equilibrium? Well, looking at K again. So remember that K is the equilibrium constant. So if K is greater than 1, that means it's product favored. Here's a great hint. Notice how the greater than sign points towards the right, towards where the products are written. So if your greater than sign is pointing towards the right, it's going to be a product favored reaction. All right, on the other side, if we had K is less than 1, notice how it's pointing towards the left, which is where we write reactants. So this is reactant favored, okay? And so this just means at equilibrium, for example, when K is greater than 1, notice we have a dramatically more products than we do reactants. Whereas in the second scenario down here, if I have more reactants than products, notice K is much less than 1. So by just looking at the value of K, you can tell me if an equilibrium system is product or reactant favored at dynamic equilibrium. So how does K react to some of the other stresses and stuff? Well, K, the equilibrium constant, is only going to be affected by temperature. And what happens is K increases, the value of K will increase when a temperature change favors the product or favors the forward reaction, whereas K will decrease when a temperature change favors the reactants, the reverse reaction. So let's take a look at this on an actual system. So looking at this one here, if the temperature is increased, the reaction will shift which direction? Well, notice heat is negative, so it's over here on the reactant side. It's listed on the right side correctly. So we know that increasing the temperature is going to cause a shift back to the left. And sure enough, it shifts to the left. Now, shifting this direction towards the left would cause the value of K to decrease. Because decreasing when we favor the reactant side, when temperature favors the left, it favors the reaction, the reverse reaction, we know the value of K will decrease. And so in this case, the value of K had to decrease because of this left shift. So there's some other terms and concepts in this unit that you need to be aware of. Entropy, S, that's how it's abbreviated, is a measure of the disorder or randomness of particles that make up a system. So just like H or enthalpy was a very important number and value, entropy is another one that you really need to be familiar with. So a transformation or shift will not proceed in any direction that reduces the total amount of entropy. It's kind of like just the natural order of the universe. So basically, things are going to have to follow a natural flow. And what's going to happen is that natural flow means that we're never going to go against creating randomness. So let's look at some of those. So entropy of a solid is going to be less than that of the entropy of a liquid, and the entropy of a gas is going to be much, much greater than that of the liquid or the solid. So a solid has basically a very orderly, straight, pyramidic, almost very, very orderly arrangement. A liquid, on the other hand, they're next to each other, they're fairly ordered, they're close together, but it's a little bit more disorganized. And then you get to a gas where it's complete chaos, and they're moving everywhere, and they're all over, and so there's a lot of randomness and disorder in a gas, whereas in a solid, there's a lot of order and organization in a solid. So when you're thinking about these, you need to know that a gas has a lot of entropy. A solid, very low entropy. Okay, so let's look at this example. Which side of a reaction has greater entropy? So we have O2 as a gas or O2 aqueous. Well, as a gas, it's totally chaos. As an aqueous, it's kind of in that liquid solution. So in this case, we know the greater entropy is going to be definitely on the left. Gas pretty much always wins. All right, which side has a greater entropy, meaning it's going to be higher in entropy, higher in disorder? The solid, which is super organized, or the liquid, which is a little bit more free-flowing? So, of course, the liquid on the right is going to have a little bit higher entropy. All right, predict the change in the entropy. Okay, so we see that we went from a solid with a gas to just a gas, and we went from 1 mole of gas to 2 moles of gas. So here we see that the entropy increased from left to right, right? We went from solid, 1 mole of gas, to 2 full moles of gas. No more solid, no more organization over here. So we increased our disorder or our randomness. All right, let's take a look at this one. We went from 1 mole of gas plus 3 moles of gas, so a total of 4 moles of gas over here on the left, to only 2 moles of gas over here on the right. So our entropy actually would, in this case, decrease because we went from 4 moles of gas to only 2. So we actually got more ordered in this case. Okay? So we're going to stop here on this video. There may be a new one for kinetics very soon, but make sure that you can now go back and fill in the rest of the guided notes for equilibrium and then work on the equilibrium worksheet. Make sure you read through those guided notes very, very carefully to help guide you through figuring out some of those problems.